Let's take a look at a couple examples here. Consider this series, and I want to figure out whether it's going to converge or not. Well, looking at this thing looks a lot like 1 over n cubed. And I know that 1 over n cubed converges. It's a p series, where p is greater than 1. So, or I could use the integral test to confirm this very quickly. So what I want to do is I want to make a comparison here. Seeing I know that this is what I'm thinking of as Bn, seeing I know that this converges, this will only be useful if this is less than or equal to this one. So what I need to happen is 1 over 2n cubed plus 1 it needs to be less than or equal to 1 over n cubed. Well, that implies that n cubed is less than or equal to 2n cubed plus 1, which is clearly true. And remember our domain, n equals 1 to infinity, so n's all positive values. So this is clearly true. Therefore, this infinite series is convergent by the direct comparison test with the series 1 over n cubed. How about this series? Well, the first thing I'm going to do is I'm going to break this up a little bit. This is the sum n equals 1 to infinity of n over n squared plus 1 over n squared, which is equal to the series n equals 1 to infinity of 1 over n plus 1 over n squared. And using some of the properties of series, I can say this is actually equal to the sum of two series, n equals 1 to infinity of 1 over n plus the sum n equals 1 to infinity of 1 over n squared. Now, I don't need a comparison test, a root test, a ratio test, because I know that this is the harmonic series. Therefore, it diverges. This is a p series with p equals 2. Therefore, it converges. So what I have is something that diverges plus something that converges, which is clearly divergent. Therefore, my series n equals 1 to infinity n plus 1 over n squared is divergent. So I really didn't need to do any type of comparison test here. I just looked at it, did a little bit of algebra, and said, oh, okay, that's what I have, and there we go.